Hello everyone, this is Kenji Fujii from Chiba Institute of Technology speaking. This time I would like to make a presentation entitled Equivalent Number of Cycles Formulation for a Base Isolated Building. First, I would like to explain the contents of this presentation. The first is introduction. Here I will explain the background and objectives of this study. The second is definition of bidirectional momentary input energy. The third is equivalent number of cycles formulation. The fourth is numerical examples. The fifth is conclusions. So let us start from introduction. In the seismic design of a base isolated building structure, the properties of an isolation layer are determined to control the peak displacement within the predetermined limit and to have a sufficient energy absorption capacity. For the seismic design, there are several energy-based seismic intensity parameters. One is the equivalent velocity of the total input energy, which is introduced in the simplified seismic design method proposed by late Dr. Akiyama. This is related to the cumulative energy demand. The other is the equivalent velocity of the maximum momentary input energy, which is proposed by Dr. Hori and Dr. Inoue. This is related to the peak displacement. In the Dr. Akiyama's method, the equivalent number of cycles is the parameters that relates to the hysteresis dissipated energy and the peak displacement. So, the motivation of this study is: what is the relationship between the equivalent number of cycles and the two seismic intensity parameters? So, in this study, the relationship between the equivalent number of cycles and the two seismic intensity parameters are formulated for a base isolated building. So, I would like to explain the definition of bidirectional momentary input energy. In this study, a base isolated building is modeled as an isotropic 1 mass 2 degree of freedom model. The superstructure of the building is assumed to be a rigid body whose mass is m. The isolation layer consists of flexible linear isolator whose stiffness is Kf and a hysteresis damper whose yield strength is Sqy. The yield surface is assumed to be circular. The behavior of isolation layer is modeled by multi-shear spring model. The behavior of isolator is assumed to be linear elastic, while that of hysteresis damper is assumed to be elastic perfectly plastic. No viscous damping is considered in isolation layer. Next, we will define the cumulative energy quantities at time t. The first is the cumulative input energy, EI. The second is the cumulative strain energy, ES. And the third is the kinetic energy, EK. Next, we will define the bidirectional momentary input energy. The bidirectional momentary input energy, which is defined in the previous study, is defined as this equation. Here, TA and TB are the beginning and end times of a half cycle of the structural response. The maximum momentary input energy is defined as the maximum of the momentary input energy over the course of the seismic event. This definition is consistent to the original momentary input energy proposed by Dr. Hori and Dr. Inoue for unidirectional response. To understand the definition of the momentary input energy, here shows an example. What I'm showing in the left is the orbit of response displacement, while in the right is that of response restoring force. The points A and B are defined as the points where the absolute value of displacement is at the local maximum. The half response of the structural response considered here begins at time Ta and that ends at time Tb. At time Tb, the maximum displacement occurs. These red curves indicate the half cycle of the structural response when the maximum momentary energy input occurs. So let me observe the response during this half cycle of the structural response in terms of energy. Three curves indicate the energy per unit mass. The red curve is the cumulative input energy, the blue curve is the cumulative strain energy, and the green curve is the kinetic energy. The increment of the input energy shown here is the maximum momentary input energy per unit mass. The kinetic energy Ek is close to zero at times Ta and Tb. Here shows the hysteresis loops in x and y directions. The hysteresis loop in x direction is shown in the left, while shown in the right is that in y direction. The half cycle of structural response begins at Ta and it ends at Tb. In x direction, the loop is regular and similar to that of unidirectional excitation, while in y direction, the loop is irregular. Here is the time history of momentary input energy. The vertical axis indicates the rate of energy input per unit mass. The area of the red rectangle indicates the maximum momentary input energy per unit mass. For the convenience, the equivalent velocity of the two energy parameters are defined. The total input energy, EI, is the cumulative energy input until the time at the end of a seismic event. Its equivalent velocity, referred to as Vi in this study, is shown here. While for the maximum momentary input energy, its equivalent velocity, referred to as V delta E, is here. Next, I would like to explain the equivalent number of cycles formulation. First, we would like to formulate the energy balance during a half cycle. Let me consider a half cycle of structural response AB shown here. During a half cycle AB, the increment of kinetic energy assumed to be negligibly small. The strain energy increment during AB is the sum of the strain energy increment of linear elastic isolator and that of hysteresis damper. Here, its behavior is assumed to be rigid perfectly plastic for the simplicity. The energy balance during AB can be expressed as this equation. Let we consider the case when the maximum momentary input energy occurs, as shown here. It is assumed that the length of the path AB is approximated as shown here. From this assumption, the energy balance during AB can be expressed as shown here. For the convenience, this equation is simplified by calculating the average in the range from eta equals 0 to eta equals to 1. The energy balance can be simplified as shown here. The simplified equation for energy balance during AB is shown here. Next, the ratio of maximum force for the flexible linear isolator to the yield strength of hysteresis damper is introduced as this equation. Using the ratio RQ, the energy balance during AB can be rewritten as this equation. Next, we will formulate the equivalent number of cycles. According to the study by Dr. Akiyama, the energy balance during a whole seismic response event is modeled as this equation. The parameter NEQ is the equivalent number of cycles. From this equation, NEQ can be expressed as shown here. So, the relation between NEQ and the two seismic intensity parameters is formulated next. The energy balance during a half cycle AB is expressed by this equation. The equivalent number of cycles is expressed by this equation. From these two equations, NEQ can be rewritten as this equation. This is the formulated equation of NEQ in this study. This figure shows the relationship between the ratio Vi over V delta E and NEQ calculated from the formulated equations. Here, the horizontal axis indicates the ratio Vi over V delta E, while the vertical axis indicates NEQ. Each curve corresponds to the value of the ratio RQ. We see that NEQ increases as the ratio Vi over V delta E increases. In addition, when the ratio Vi over V delta E is larger than the square root of 3 over 2, NEQ increases as RQ increases. So, let us move to the numerical examples. First, I would like to explain the structural model parameters. In this study, 3 parameters are considered. The first is the seismic isolation period, TF. The range of TF is set from 3.0 to 5.0 second. The second is the ratio RQ. 8 values are set for RQ from 1 over 2 to 8. The third is the stiffness ratio alpha. Here, alpha is set to 0.01 and 0.10. So, 176 models are considered. This table is a list of ground motion records considered in this study. 10 ground motion records, including near-field and far-field earthquakes, are considered. These two ground motions are explained as the example 1999 TCU and 2003 TOM. Here is the examples of recorded ground motion sets. Horizontal major and minor components defined by alias is shown here. The duration of the ground motion of 1999 TCU is short, while that of 2003 TOM is long. This figure shows the linear bidirectional VI and V delta E spectra of two ground motion records with 10% viscous damping. The spectra of 1999 TCU are shown in the left, while those of 2003 TOM are shown in the right. This figure indicates that the ratio Vi over V delta E is small in case of 1999 TCU. In addition, the Vi over V delta E is larger in case of 2003 TOM. Next, I would like to show you the validation of NEQ formulation. What I am showing to you is the comparisons of the equations and the numerical results in case of RQ equals 1. The result of the case alpha equals 0.01 is shown in the left, while those of the case alpha equals 0.10 is shown in the right. As shown in these figures, the proposed equation is satisfactorily accurate for both cases. Here is the comparisons in case of RQ equals to 2. As shown in these figures, the proposed equation is satisfactorily accurate for both cases. Next, here shows the comparisons in case of RQ equals 1 over 2. As shown in the right figure, the proposed equation is unconservative. In case of alpha equals 0.10, the proposed equation is still satisfactorily accurate in case of alpha equals 0.01 as shown in the left. Finally, I would like to move conclusions. In the study, the relationship between the equivalent number of cycles and the two seismic intensity parameters are formulated for a base-isolated building. The formulate equations is shown here. The parameters of this equation are the ratio of the equivalent velocity Vi over V delta E, and the other is the ratio RQ. The second conclusion is the formulated equation implies that NEQ increases as Vi over V delta E increases. And when Vi over V delta E is larger than the square root of 3 over 2, NEQ increases as RQ increases. And the third is that the accuracy of the formulated equation is satisfactory when RQ is larger than or equal to 1. This is the end of my presentation. Thank you very much.